In this video, we're going to draw the Lewis structure of H3PO2. We're also going to discuss if it's polar or nonpolar. We're going to talk about the molecular geometry and the bond angles as well. Now, H3PO2 has two different forms, but before we get into that, let's look at the number of bonds that each atom likes to form. Let's start with phosphorus. Phosphorus has 5 valence electrons. Oxygen has 6 valence electrons and hydrogen has 1. Phosphorus wants to have 8 electrons. Right now it only has 5. It needs 3 more to get to 8. So phosphorus likes to form 3 bonds. However, phosphorus can also give away its 5 valence electrons. And if it gives away its 5 valence electrons, it can do so through the formation of 5 bonds. So typically phosphorus usually likes to form anywhere between 3 to 5 bonds. Oxygen likes to form 2 bonds. It has 6 valence electrons and needs 2 more to get to 8. Oxygen cannot form 6 bonds. Because it's in the second row, it cannot have an expanded octet. It cannot have more than 8 electrons. Elements in the second row only have the 2s and the 2p sublevels available to them, so they cannot have more than 8. Phosphorus is in the third row, and it can have an expanded octet. It can have more than 8 electrons. Due to the fact that third row elements, they can have the 3s, 3p, and the 3d sublevels available to them. Hydrogen is in the first row. First row elements cannot have more than 2 electrons. And so hydrogen only needs 1 more to fill its first energy level. So hydrogen likes to form 1 bond. So because phosphorus can potentially form the greatest number of bonds, we're going to put it in the middle. Now, in one structure, phosphorus can have 3 bonds. So let's place the 2 oxygen atoms first. In order for phosphorus to have 3 bonds, each of these, we need a hydrogen here as well. We have to put a single bond around 3 different elements. Now, oxygen wants to have 2 bonds, right? And we have 2 more hydrogens because we have a total of 3 hydrogens in the structure. So we're going to add a hydrogen to each oxygen. Actually, let me draw it a little differently. Whenever oxygen has 2 bonds, we need to add 2 lone pairs. And whenever phosphorus has 3 bonds, we need to add 1 lone pair. This is the Lewis structure, or at least one form, of H3PO2. As we can see, phosphorus has 3 bonds, oxygen has 2, and hydrogen has 1. If we add up the valence electrons for H3PO2, hydrogen has 1 valence electron, phosphorus has 5, and oxygen has 6, and there's 2 of them. So 3 plus 5 is 8, 6 times 2 is 12. So the total is 20. Let's make sure that we have 20 electrons. Every bond represents 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we have the right number of valence electrons. Now there's another way to draw H3PO2. And in this Lewis structure, phosphorus can have 5 bonds. Hydrogen can only form a single bond, but oxygen can have 2 bonds. This is another acceptable Lewis structure. As we can see, phosphorus has 5, every hydrogen has 1 bond, and every oxygen has 2 bonds. As long as you can meet those characteristics, that Lewis structure is fine. And it turns out that H3PO2 can convert between these 2 forms. Let me show you. So let's start with the first one that we drew. One molecule can react with itself. So this lone pair is going to be used to grab this hydrogen. That hydrogen is relatively acidic. And oxygen, because it's more electronegative than hydrogen, when this OH bond breaks, those electrons will return to that oxygen atom. And so what we're going to have is an oxygen with a negative charge. And we still have a lone pair here. Now, at this point, this molecule right now, I'm going to draw it here. It's going to look like this. So now there's a hydrogen atom. This lone pair was used to form the bond with this hydrogen. And now phosphorus has a positive charge. If you want to calculate formal charge, it's the valence electrons minus the number of bonds and dots. Now some textbooks may have a different formula, but I think this one is just a very simpler one to use, but you get the same thing. The results are the same. Phosphorus has 5 valence electrons. In this structure, it has 4 bonds, no dots. So 5 minus 4 plus 1. Because it has a positive charge, phosphorus can accept a pair of electrons. So one of the oxygen atoms, we'll choose this one, is going to use this lone pair, form a double bond. And I'm going to draw that resultant structure right here. So we're going to have a double bond and a hydrogen, one lone pair, and a plus charge. As you can see, it's getting very close to the other form. We're almost there. So now this oxygen with a negative charge, it wants its hydrogen back. So it's going to grab it from this hydrogen, and this bond is going to break, returning those electrons back to that oxygen. So now we have, so this molecule, I'm going to draw its resultant structure. It's going to look like this. This is the other form of H3PO2. And this molecule, since it gained a hydrogen, it looks like this again. So to summarize it, we see that H3PO2 has 2 different forms. It's interconvertible. Now, as we mentioned before, phosphorus can have 3 bonds or 5 bonds. And in this structure, it has 3. And here it has 5 bonds. Now let's talk about the molecular geometry for these 2 molecules. Now, how would you describe the molecular geometry for each one? What would you say? Now, because of the lone pair, this looks like NH3. And as a result, it has a trigonal or trigonal pyramidal structure. The bond angle for NH3 is around 107, so we should expect this particular form to have a similar bond angle. Now, for this one, there's no lone pairs on the phosphorus, so it has a tetrahedral molecular geometry, which usually has a bond angle roughly around 109.5. Now, what about the hybridization? What's the hybridization around the center phosphorus atom? In this structure, phosphorus has 3 bonds, 1 lone pair, so it has like 4 groups. When an atom has 4 groups, its hybridization is typically sp3. Notice that the exponents add up to 4. And for oxygen, this oxygen has, let's see, 2 lone pairs, 1 atom. It's attached to 1 phosphorus atom, so it has 3 groups. So it's sp2 hybridized. This particular oxygen right here has 4 groups. It has 2 lone pairs, and it's attached to 2 atoms, the hydrogen and the phosphorus. So this oxygen has 4 groups, so it's going to be sp3 hybridized. And this phosphorus is attached to 4 atoms, so it's also sp3 hybridized. So that's a quick way in which you can tell the hybridization of a certain element. But now the last thing we're going to look at is if these molecules are polar or nonpolar. So let me just redraw the Lewis structures. Now, the phosphorus-oxygen bond is very, very polar. If I remember correctly, phosphorus has an electronegativity value, I believe around 2.1, but for oxygen it's like 3.5. So the electronegativity difference is greater than 0.5. It has to be at least 0.5 for it to be polar. So this bond is extremely polar. Oxygen is going to pull the electrons toward itself, acquiring a partial negative charge, and phosphorus is going to have a partial positive charge. Whenever you have separation of charge, you have a polarized substance. The phosphorus-hydrogen bond is not very polar. Both phosphorus and hydrogen roughly have an electronegativity of close to 2.1. So the electronegativity difference is almost zero. They're not exactly the same, but these are estimated numbers. But that bond is relatively nonpolar. So we only need to draw the dipole moment for the phosphorus-oxygen bond. Notice that these arrows, they don't cancel. They point in this general direction. So because there's a net dipole moment, it's going to be polar. Anytime you see OH bonds, you have hydrogen bonding. And for hydrogen bonding, or any substance that can form hydrogen bonds, are usually polar substances. Now you might be wondering, okay, what if we draw the Lewis structure like this? Wouldn't the dipole moments cancel? Wouldn't these two point in opposite directions? You might think, hey, this is a nonpolar substance. But keep in mind, if you were to draw it this way, you have to consider the OH bond as well, and not just the phosphorus-hydrogen bond. So even though it may appear as if these two cancel, you also have this bond as well. Oxygen is more electronegative than hydrogen. That hydrogen bond is extremely polar. And so these three arrows, they don't completely cancel. And another reason, these two arrows are not anti-parallel. What we have is a tetrahedral geometry, and so the bond angles aren't 90 degrees. So this structure should look more like this rather than being linear. It should be at an angle. So if we only focus on these two arrows, they wouldn't cancel because they're not directly opposite to each other. So what does this all mean? Basically, this molecule is polar. We have a net dipole moment. The arrows, they don't completely cancel. So we have a polarized substance. So that's it for this video, and thanks for watching.